Good morning, everybody. Welcome back to another episode of Mastering Diagnostics with yours truly, Brandon Steckler, technical editor of Motor Age magazine. Now, today's episode is going to be about maximizing scan tool functionality for a faster return on investment. And here's where this stems from. I've spent nearly 30 years in the shop environment, and I see technicians and shops have extremely expensive tooling, and no need to name names, but these tools are expensive. But I frequently see them using the scan tools, for instance, to merely extract DTCs or clear DTCs and build an occasional PID list. But they don't truly leverage the power of that scan tool. So what I'm getting at is it's a tremendous investment, a necessary investment in tooling, but they never see their return on investment. And that's sad. And it's certainly discouraging, and it prevents them from wanting to invest money later. But my biggest concern is that everybody gets their return on investment and optimizes the tool's functionality. So what does it take to purchase a scan tool? What is going to push us over the edge to complete that purchase, to lock in and seal the deal? We truly have to find a balance between what it costs to purchase the tool and maintain the tool versus what the tool pays for. In other words, with Massachusetts Right to Repair Act, we as technicians in the aftermarket have access to factory data and access to factory tooling if we choose to make that purchase. But for me to purchase a tool for a day or a few days or maybe even a week is certainly a little easier to swallow than to make the purchase for an entire year if I don't use that scan tool on a regular basis. So the idea is to get the most bang for your buck, so to speak. Now, we all are well aware that tools come in many configurations. Some are downloadable and PC-based. Others ride on the shoulders of an Android tablet. They come in many configurations, and the cost of some of the hardware can be truly expensive. So cost is definitely a huge factor. But the point is, no matter what tool we're purchasing or for what purpose, that tool functionality must justify the cost. So how is it we can do our research? We can reach out to our friends, our industry peers. We can read magazines and tool reviews from some of our friends on YouTube and LinkedIn and other information sources like that. We can reference scan tool shootouts, meaning maybe the scan tool manufacturers or tool dealers will allow us to take that tool for a test drive, so to speak, and compare it to the tools we already have or the tools we're looking to purchase. My colleagues and good friends at Professional and Tool Equipment News magazine put out a scan tool buyer's guide each year, and there'll be links for that guide below and from previous videos where we referenced this P10 scan tool buyer's tool guide. Today, I want to talk about a specific tool that I have in my hands from my good friends at Bosch Diagnostics. And it's sitting right there behind me over my shoulder. This is the Bosch ADS 625X handheld scan tool and diagnostics system. What I love about this tool is it's intuitive to use, first and foremost, meaning the first time you pick it up, it behaves how you'd expect it to behave, and you navigate it the way you'd expect to navigate the tool. Now, the tool itself is based on an Android platform. It's very lightweight, it's relatively robust, and the screen is very easy to see. It has some really neat functions that we're going to discuss today, and the point of the video is to leverage as many scan tool functions as possible to make diagnostic decisions where it counts most, and that's right at the driver's seat, particularly if you're a drivability tech like myself. Because let's face it, there could be a dozen or more things, components, failures that could cause the very same symptom we're experiencing now. And if I chose to dive into all 12 or 15 or 20 of those components or circuits or systems and start investigating them, their functionality, in some elapsed time, I could probably find the root cause of the fault. But the point is, being accurate is only one half of the equation. We need to be efficient as well, because every one of our bays in the shop is a business within a business, and those work bays have to remain profitable for the business to prosper overall. So being able to do things like an all module DTC scan and leverage service information and wiring diagrams right from the driver's seat serves us well. It prevents us from having to leave the vehicle and walk back to our PC, which might be located at our toolbox or our desktop or a dedicated research area within the shop. All those things take time. Being able to capture a fault and prove where the fault may lie, try and triangulate its location through bidirectional control, allowing the scan tool to take control of PCM functionality and drive systems as a whole. And we've seen that in previous videos as well. But to then take control with that scan tool through bidirectional control, mode 8 of the scan tool, and actuate individual components, making them work, monitoring their functionality, perhaps with a lab scope and amp probe, or perhaps even just listen audibly for their function. All of these creature comforts, if you will, I find to be extremely beneficial, especially in the name of accuracy and efficiency as well. To be able to save all that information natively on the device, or perhaps uploaded to the cloud via a Wi-Fi connection. Again, right from the driver's seat of the vehicle, saves a ton of time. Whether we're talking about screen captures or data movies, all these are uploadable and shareable to a digital vehicle inspection report, should we choose to do so. Heck, even email them to yourself on perhaps a Google Drive. So I want to show you by way of example, because you know me, I never try and sell anything. I'm not a salesperson. I'm a technician just like all of you. And you guys, you ladies and gentlemen, are what mean most to me in this industry. So I'm going to give you my honest opinion on this tool's functionality. So we are going to be referencing my 2009 Acura RDX, and I created a fault. I'm not going to tell you what it is, but it's a real world fault that we're experiencing. And the fault I'm about to tell you about is a common fault with this vehicle, but for several different reasons. Meaning I could have the fault I'm experiencing due to a bad component, or the fault I'm experiencing due to a bad switch, or the fault I'm experiencing due to a wiring issue, or even a hydraulic circuitry fault like a restriction in an oil galley, or even just low or poorly maintained oil in general. So we are going to leverage the power of the Bosch ADS 625X to analyze this vehicle's problem in a real world scenario. And you will see not one single time preliminarily do I have to leave the driver's seat. It's only after I get a great sense of direction on where the fault may lie do I commit to opening the hood and investigating the system. And why did I choose to do it then? Because I had justification to do so. The data captured from the ADS 625X, the wiring diagrams, and the service information that I was able to access from the driver's seat made all this possible. They served as puzzle pieces to an overall giant puzzle that I had to assemble mentally. So we're going to talk to the customer and determine what the fault is. And like any good investigative diagnostician, we're going to reproduce this concern. We're going to go on a road test and capture the fault. And by way of the customer's perception, the fault, as described, could be a number of different things. It could be a fault related to the engine, a fault related to the ABS or vehicle stability assist control system, and it could even be related to the automatic transmission. All these are real world and very possible for a fault in a vehicle of this age. We're going to leverage the power of the DTC scan to give us a generalized direction on where the fault may lie. We're going to capitalize on a customized data PID list, one that allows us to eliminate unnecessary information so we could focus on the fault and the story to be told. We're going to reference service information and wiring diagrams to get an idea of what it takes to set the fault, the components related, or what I like to call the players in the game, and an idea and overall roadmap of the circuitry and the component location so we can determine the best place to test when that time comes. We can save this information internally and review it at the comfort of our toolbox or our PC, even at home or anywhere across the world. With an internet connection, we'll be able to leverage the power of Mode to the scan tool to force system operation and bidirectional control of individual components to see those components function or listen to those components function. And all this in the name of science to determine preliminarily where we want to invest our time under the hood when the hands-on tests come to be and are justified performing. The idea is to reduce our time spent under the hood, testing everything related to the entire system. By gathering information pertaining to system functionality, the thresholds necessary to set the fault, the information demonstrating the system's operation, and the feedback information providing that the system is or is not functioning properly. All this stuff leads to the hands-on testing, the secondary testing we perform once we've committed to doing so. So let us head out to the car now. So a road test of the vehicle was conducted, and just as the customer described, upon acceleration from a stop, when you get into mid RPM range, I'd say around 2,500, 3,500 RPMs, the vehicle bucks violently several times and will not relieve itself of this symptom until you back off the accelerator pedal. It idles fine. It cruises just fine. Going down the street gingerly or even moderate acceleration, again, no problem. But as you begin to accelerate harder, the vehicle bucks violently. And so it begs the question, are we dealing with a drivability symptom that's related to an engine? The valve train, perhaps? Are we dealing with a situation where we've got a misfire, a secondary ignition misfire, and spark is deviating away from internal to the combustion chamber, where it should be, and perhaps deviating out the side of a ignition coil boot or down a carbon track of a spark plug? Perhaps we're dealing with a transmission issue, a loss of hydraulic pressure, and a clutch is slipping. All of these are possibilities that surface. And I'll show you here in a second. The cluster's lit up like a Christmas tree. We've got a check engine light illuminated. We've got vehicle stability assist warning indicators illuminated. And our heads-up display has indicated there's a problem requiring diagnostic investigation. So we're going to begin our process with an all DTC scan. And I mentioned that like I did earlier because especially on today's vehicles, these systems survive on a virtual platform. There are many systems configured to network together to accomplish goals. And in this case, propelling the vehicle down the road under load, we could easily be dealing with a transmission slip issue, an engine problem. When I say engine, I mean a base engine problem. Keep in mind the valve trains that exist today incorporate things like variable cam timing and variable valve lift and duration, and all these are driven off that lifeblood, that hydraulic oil pressure. So those could be at fault as well. So again, my point of stating that is the blanket statement that an all DTC scan, I wouldn't just say is a good idea. It's absolutely necessary on today's vehicle, especially due to the states of default that occur when faults are present. The drivability symptoms we're feeling may not be the problem at all, but simply the fact that the vehicle is in a state of default. So we're going to first leverage our Bosch ADS 625X to, right from the driver's seat, scan every node on the network and look for faults to surface, again, giving us a clue on where to begin our diagnostic journey. So we'll start with the scan tool at the main menu and self-identify the vehicle. If we click on Diagnostics, the option for Auto ID is there. The scan tool is going to reference Mode 9 of our OBD2 system to pull the VIN number and configure the scan tool to match our vehicle. And in just seconds, it's identified as an 09 RDX. I'm happy so far. we're going to perform our DTC check. And we have the option to read any one of these nodes individually, which of course would save some time if we already knew what the problem was. But instead, I'm going to select all. And as you can see, the ADS 625X is scanning all the nodes in turn, one at a time, and it's going to create a report for us on which nodes have failures and what those failures would be. So as we can see here, our scan is complete. Our nodes that don't have any stored DTCs have green check marks. It's fairly intuitive. Our nodes that cannot be scanned are indicated with a warning triangle and exclamation point in the middle. In this case, this vehicle does not have electric power steering. So quickly I can see which nodes are faulted. Of course, the engine's faulted. We've got a DTC P2646 pertaining to rocker arm actuator control system performance, or stuck off for variable cylinder management system. If I go down to electric brake vacuum pressure, we've got the same DTC. Four-wheel drive also stores a DTC pertinent to the fault we have. This one indicates functional abnormalities of fuel emission or automatic transmission. And then ABS states the engine control module or powertrain control module has a related malfunction. So we're going to pursue the engine fault, the P2646 pertaining to the rocker arm actuator control system performance of stuck off variable cylinder management system. So we have to keep in mind with the DTC stored in multiple nodes like we've seen in this vehicle's configuration, most of the codes appear to be symptomatic. In other words, a result of the underlying fault found in the engine controller, which makes sense because we are in fact experiencing a drivability problem. But to assume that without checking would be foolish. Many a times I've had symptoms I've chased only to be a symptom of a default strategy, meaning the underlying problem was not in the area I was investigating. So what we're going to do is we're simply going to gather some information, again, right from the driver's seat. Since this scan tool is networked wirelessly to a Wi-Fi connection, I have access to service information powered by motor. So simply clicking on the Details button will bring us information pertaining to the DTC. The screen populates with a function known as Code Assist. Code Assist comes from history reports of previous technicians stating when they encountered this same fault, what fixed it. And in two cases here, it was pertaining to the oil hydraulic system. Either low, dirty, or worn out oil allowed this fault to occur. But what I'm going to recommend we do is we revisit a repair source to find information pertaining to this DTC so we can learn more about it. So the ADS 625X from Bosch pulls the information over from mode 9 of our scan tool functionality, and it populates the search information criteria right there for us. We've got information pertaining to the diagnostic trouble codes we are experiencing. So leveraging the ADS 625X to access service information right here from the scan tool interface at the driver's seat, we're able to locate some just-in-time training, some information based upon the system we're working on. And what we learned here is that the P2646 DTC that we have stored means that the PCM doesn't like what it sees. It uses a high-side-driven solenoid to actuate a spool valve. When the PCM wants VTEC, or variable timing electronic control, said another way, variable lift and duration of the valve train, it energizes the solenoid. When the solenoid is energized on the high side, hydraulic pressurized oil is delivered through the rocker arms to cause a change in the valve train operation. But at the same time, that same hydraulic oil pressure acts upon a switch. And what we learned about referencing the wiring diagrams is that the switch is a normally closed switch, meaning under, I'll call it normal, low-end engine operations, the switch is closed, and when that switch is closed, a voltage reference leaving the PCM references ground and is pulled low. So I remember it like this as I read it. Low engine load, low VTEC pressure switch signal. High engine load, when VTEC is commanded, we should have a high pressure switch signal. That switch should open under hydraulic pressure and remove the ground reference, remove the path to ground for the switch signal leaving the PCM. So knowing that, let's go for a road test, configure the scan tool to see the appropriate data we need to see to make this diagnostic decision, and head us down the right path for diagnostics without wasting any time. So we're simply going to build the data list we choose to see. We're going to go to Diagnostics. Going to choose Recent Vehicles, the RDX. I'm going to go into Data Stream. I'm going to select Engine. And I'm going to scroll down till we find 2 particular PIDs. I'll build a customized data list so we don't have to look for everything. That's going to speed up the refresh rate of my scan tool, plus make it less overwhelming for me mentally while I'm trying to make decisions about the functionality of this vehicle's valve train. Now, I'm interested in 2 particular PIDs. One PID is the command to the VTEC solenoid. So I know that the PCM intends to actuate VTEC high output range. 2 is the feedback, the pressure switch status for the VTEC system. But I always like to gather information that tells a story, so I want to know engine load and RPM as well. Do I need that data? No, but because I can graph multiple PIDs at the same time, it helps to tell the story later on down the road when I'm not in the vehicle. So I'm going to select calculated load, engine speed, VTEC solenoid, and VTEC pressure switch. But I'm also going to add oil pressure switch in case there was a fault there. When I select OK, the scan tool reconfigures the data to show me only what I wish to see. Here we can see it in numerical value, but I like to look at things in graphical format. It makes it easier on the eyes. As you can see, our buffer is filling with data, and that buffer will continue to fill until 200 frames of the scan tool buffer are occupied. And at that point, the oldest information is voided to make room for newer information. So we are going to expand this information. We've got bar graphs, we've got line graphs, and we've got switched status. So what you need to know is that our VTEC pressure switch indicates on, as in the switch contacts are on, and our VTEC solenoid is commanded off. What we should expect to see under the appropriate load and RPM value is the VTEC solenoid be commanded on and the VTEC pressure switch to change to off. So in other words, they should flip-flop. So I am going to expand this data. And we're going to look at our VTEC solenoid. So again, as I accelerate the vehicle, we are going to expect to see the VTEC solenoid change to on, and at the same time, our VTEC pressure switch to change to off. So I'm going to accelerate. On, but this stays on. So we've experienced our problem. So the ADS 625X quickly showed us the information we needed to see to make a diagnostic decision about an overall functionality of the VTEC system, a unique system pertaining to the valve train configuration on this Acura RDX 2.3-liter K-Series engine. What we now need to do is make a decision. Do we want to start going under the hood and looking for potential faults? In other words, are we dealing with an oil issue? In other words, oil is low or oil is contaminated? Are we dealing with a solenoid issue, as in the PCM intended to actuate the solenoid, but there's an electrical circuit fault in that solenoid's path, or the solenoid itself is faulty? Perhaps there's nothing wrong with the oil, nothing wrong with the PCM or the solenoid itself, but an issue with the hydraulic circuitry pertaining to the VTEC system. Maybe there's an issue with the feedback pressure switch. These are all questions we have, and to investigate each one of them individually would certainly lead us to the root cause of the fault. However, how much time would that take? What I'd rather do is use my head and leverage the power of the Bosch ADS 625X some bidirectional control, some system tests, and then individual component tests to see if the system is indeed attempting to work as designed. If we carry out the test and it shows a fault, depending on what the fault is, we can pursue it in that direction instead of pursuing everything at once. So let's get started. So we'll back out and we'll go to our special tests. Now that special test is going to allow us to access multiple points on the vehicle depending on what test we are trying to carry out. In this case, of course, we're going to select the engine tests. And particularly, we want to see the tests pertaining to our VTEC system of our valve train. So our special tests are all configured here for selection on left-hand pane of the scan tool. We're going to click on VTEC tests, and we're going to allow us to carry out, first and foremost, the VTEC solenoid test. Now, the VTEC solenoid tests allows our ADS 625X to command the PCM to force the VTEC solenoid to energize under higher RPM. And if there is no change in the system's functionality, we then have to pursue the fault further. So this is a really quick, easy, generic test we can do from the driver's seat before we invest any time under the hood hunting sporadically for possible faults that could exist. I want to do that only when I know what fault I'm chasing. So we simply follow the on-screen commands from the ADS 625X during this bidirectional control system test of the VTEC system. It tells us the engine has to be off. So key on engine off. We're going to continue the test. It's going to activate the VTEC solenoid and we listen for clicking. So let's listen. I heard it solenoid click. You probably didn't hear that on camera. And I heard the solenoid turn off. We'll try it again. The solenoid indeed clicked. And it clicked off. So with this test carried out, the VTEC solenoid proves to be functional. That tells us a lot. It tells us the PCM sees the request from the ADS 625X, processed it, create the output to drive the solenoid circuit is intact, and the solenoid itself has continuity, meaning no opens take place. And there's enough electrical current in the system for the solenoid to shuttle. But what we don't know is their pressurized oil behind that solenoid. So let's carry out the rest of this VTEC solenoid bidirectional control system test. So the VTEC test is now what we're going to carry out. Once again, key on engine off. And it tells us we have to clear DTC before the test begins. So the DTCs have been cleared. And it tells us to keep it between 2,000 and 3,000 RPMs. So I'm elevating the RPMs now. What this is doing is producing adequate oil pressure before we initiate the test. And here we go. Now it tells us to elevate it more. That tells us to release the throttle. And it tells us to do it again. And as we can see, our solenoid's being commanded on, and there is no change in switch status. So it offers us some possible failures. But let's talk about some logic for a moment. So again, from the driver's seat, we were able to conduct some bidirectional control system tests. By first performing the VTEC system test, we were able to take control of the solenoid with elevated engine RPM and sufficient oil pressure. And through command of the solenoid, we waited to see if the system functioned. Now, there's two things I can tell you about this system's functionality. For one, I heard a change in engine pitch as the solenoid was energized. That tells me a positive change occurred. The pressurized hydraulic oil was driven past the solenoid to activate the VTEC valve train and allow it to go into high output operation. That's something we could hear audibly from the driver's seat. We also witnessed the screen from the driver's seat showing that there was no change in feedback switch status. By shutting the engine off and energizing the solenoid, we can hear it click. So it proves that the system is functional, but we are likely dealing with a feedback switch circuit fault. Now it's time to open up the hood and investigate further. So we're out under the hood now, and we've committed to testing. It makes sense to do so at this point in time because we've proved, using the easy-to-grab information leveraged from our Bosch ADS 625X, that the fault is indeed related to the VTEC pressure feedback switch or the circuitry in which it resides on. So, under the hood, we've got our ADS 625X, and right down here is the VTEC pressure switch, and it's quite difficult to get to. But as you can see, even with the switch disconnected, my VTEC pressure switch status says on. On meaning contacts closed, referencing ground. But with the switch disconnected, there should be no reference to ground. So again, using the easy-to-access wiring diagrams and component locator from our information system powered by motor, I was able to easily locate the pertinent connector and terminal and related wire color for our VTEC pressure feedback switch. Leveraging our Bosch MMD540H hybrid multimeter, we're simply going to check available voltage at that sensor signal terminal. Proving first that we are referenced to a good battery ground and voltage source, our meter is reporting source voltage at approximately 12.4 volts. Our VTEC pressure switch circuit, key on, engine off, as we are right now, should read voltage high because our ground reference is disconnected via the disconnected switch. But as you can see, when we touch it, we've just got several millivolts on it, indicating either a path to ground or poor output from our PCM. So by inspecting the harness between our PCM and our pressure switch, we found that the harness was rubbed through behind the engine block due to a poorly located wiring harness. The harness allowed the VTEC pressure switch signal wire to rub through and find a path to ground, pulling that signal low, indicating to the PCM that the VTEC pressure system was not functional. But when we manipulate the harness, we are able to get this VTEC pressure switch status to change from on to off, concluding that we found our issue. We are now going to complete our repair and repeat the same test we performed earlier to infer that the repair solved the root cause fault. We're going to simply capture the same data we looked at before to infer that the system is now working, both the command from the PCM and the signal change from the feedback switch. We'll go back into our data stream again and select the information we found pertinent. Engine. And all we really need to see at this point in time, once we customize our data list, is our VTEC solenoid command and the feedback from our VTEC pressure switch signal. We'll expand the data once again, expand it again, and repeat our road test. What we should expect to see is the VTEC solenoid commanded on, and as a result, the VTEC pressure switch status should change to off. And there we have it. So, as you can see, the Bosch ADS 625X is a more than capable scan tool. It's lightweight, it's easy to hold, it's easy to navigate, it's intuitive to use. Being able to access just-in-time training right from the trenches is a game changer because it saves a bunch of time and really boosts efficiency and confidence about the testing you're about to perform. Being able to use scan tool data in a graphical format allows for that action-reaction comparative measure so you can see the story about the system's functionality being played out. All this saves time because it allows you to build a diagnostic game plan right from the driver's seat. And when you have an idea about how the system works, leveraging the scan tool's bidirectional controls and system tests allows you to prove or disprove your theories. All this before investing the time come testing underneath the hood when you need to do so. It all suddenly becomes justified. So circuit testing like voltage drop and continuity tests of components suddenly makes sense, and you're no longer shooting from the hip. With a machine gun, you're firing with accuracy like a marksman, leveraging a sniper rifle. It's scan tool features like this that come in extremely handy when it comes time to make that decision on which scan tool diagnostic platform is right for you in your shop. Being able to justify the cost because the scan tool can show you a really quick return on investment is what it's all about, because that's exactly what it is, an investment. These scan tools cost money, but it takes money to make money in our industry. And as long as the tool makes you more money than it costs, you're doing the right thing for you and your shop. But you won't see the return on investment with any tool unless you understand what the tool is capable of and you leverage those features. Scanning DTCs to determine a system that the fault resides in, leveraging scan tool data to determine what the fault is, bi-directional control to help you determine what area of the circuit or system is faulted, accessing service information for wiring diagrams and component location, connector pinouts. All these come together to help you build that diagnostic game plan for the driver's seat. Because it's this research that develops anticipation on what you should expect from the test results you gain when you actually get underneath the hood and start testing hands-on. So don't be a sheep to flowcharts. Use them to your advantage to determine thresholds and pertinent information like resistance values and testing criteria, and allow the data you gather from the scan tool to help you make diagnostic decisions. This leads to a true understanding of how things happen and why, which gives you confidence. And when you have confidence and you have efficiency, you have less comebacks, you make more money, happier customers, and an overall better day at work. And when the right tool and affordability of that tool come together, you see that faster return on investment, more efficient technicians, and a higher producing business. Brandon Steckler, technical editor of Motor Age magazine, and I thank you for joining me on this episode of Mastering Diagnostics featuring the Bosch ADS 625X.